Hi, we are going to be looking at determination of internal forces on a statically indeterminate truss system using the force method, or the so-called lever in Chinese language. So, as usual, we begin by laying down the steps that we consider in our process of calculation. The first one is that we find the excess member of the truss that makes it to become statically indeterminate. After finding that, that excess member there becomes the one to bear the unit force. So for such a system of a truss, we know that to test whether it is statically determinant or indeterminate, what we need is that we first look at the type of support that it has. Here we see that it is simply supported, as in like it has got three reactions. So what we do, we drop the supports since it's only under three support forces. Then after doing that, we look at the system and try to analyze whether it is indeterminate or determinate. And then if it is indeterminate, we have to determine the degree of indeterminacy. So for the sake of this one, we know that we can begin by working with a triangle, which we know that a triangle is a statically determinant structure on its own because it has got no degree of motion. Then when we add a two-member diagram, that is, if I have a structure that is statically indeterminate and then I add a two-member structure on it, it does not alter anything about it. So to the triangle, if at all I do add on this two-member system, it is still a statically determinant structure. Then after doing that, I can still add on a two-member system, that is this one here. It still remains statically determinant, and with the same I still add on this one here like that, which is also still statically determinant. Then from observation, we see that we have one extra member that is left that isn't used, and that is the member BE, this one here, the member BE. So this member BE becomes our member that causes the system to be statically indeterminate, or the excess member. Thus, in our calculation, it is on such a member that we shall add a unit force. That is, if I give it that direction of action, I would be calling it x1 is equal to 1. Yeah, so therefore, for this system, we have only one degree of indeterminacy. If in case we had two members that were excess, it would have been a 2 degree of indeterminacy. So we go on and we look at our next step after that is done. The next we move on and find the internal forces due to the action of this unit force alone. And after finding the internal forces on the structure due to the unit force, we also go on and find the internal forces due to the action of the force on the system alone. Then after doing that, we come and solve for x1 from the equation sigma 11 x1 plus delta 1p is equal to 0. Then after doing that, we come and carry out the last evaluation, that is of the final internal forces from n is equal to n1. The n1 represents the internal forces from the action of the unit force, then times x1 that we get from this equation here, and then lastly we come and add what? We come and add our NP, that is the internal forces from the action of the original loading on the system. So I hope the steps are clear. The next, let's look at an example. So assuming that you've been given this truss system, and then we're required to find the internal forces on each member, and then the dimensions are given as follows, and the EA has been given to be a constant. So what do? We begin from the first step. We say that we first need to come and find the member that causes the system to be statically indeterminate, and then after finding that member, we do add a unit force onto that member, the unit force given by x1. So as earlier on said, from our observation, like we shall see that the member, we can either choose a member BE or CD to be our excess member. Yeah, so we add on our unit force as follows. That is a unit force x1 is equal to 1, and then it's acting in that direction as indicated by the arrows on the system. So our next step after doing that, we say that we need to come and find the what? We need to come and find the internal forces on the structure due to the action of the unit force x1. So if we have to do that, we say that the original loading is not supposed to be considered on the diagram. So from our observation, we see that on this system here, we only do have the action of the unit force x1, like we do not have any action of an external force. Therefore, the reactions that they support would be equal to S0. So we have no reaction here, as in like the reactions are equal to S0. So if the reactions and the support are equal to A0, automatically we shall know that the forces onto the rod CF and then EF are 0, then that of AB and then AD would also be equal to A0. Then after doing that, we shall find that now we are only left with what? We are only left with this inner square here, like that, of which we need to come and find the internal forces. So to now find our internal forces on the remaining part, what we are going to do, let's say for example begin by using the joint B like that. So at joint B we have it connected to the rod BC, so the internal force would be N BC, and then rod, it's also connected to the rod BD, so it has got internal force N BD. Then besides that's connected to that slanting rod which has got a force of x1 is equal to 1. So let me just name it as having a force of 1. So to be able to find the forces on the NBC and then NBD, I need to come and resolve this unit force here into the x and into the y direction, like that. So when I resolve it into the x and into the y, since this triangle here that we have is an equilateral triangle, we know that the forces would be equivalent to root 2 times 1, which gives us approximately 0.7. That is in the x and then also in the y direction. Yeah. So after doing that, now we come and find our NBC by summing the forces in the x direction. So NBC plus 0.7 is supposed to be equal to 0. Therefore, NBC is equal to negative 0.7. Likewise, you come and do the same for the forces in the y. Then we come and find out that our NBD would be equal to negative 0.7. Thus, we come and indicate our forces on this truss. This is negative 0.7. This is also negative 0.7, like that. So, using the same principle, I come and I take a point such as C, and then when I follow up the same procedure, I'll find that now the force on the rod DC would be equal to 1, and then on the CD it will be equal to negative 0.7, then on DE it would be equal to negative 0.7 also. Thus our internal forces on the N, let me label the drawing as N1, on our N1 has been found. So next we come and find internal forces on the truss due to the action of the original loading, that is the load of 30 Newton. So for this time our system would be as shown. So the first observation that we have to make is that since our rod BE has been BE, that is this one here, the BE has been cut, so that means that it will be having an internal force of what? Of 0. It won't be carrying an internal force. So next we come and find the reactions on the structure since we have an external force. So here we shall be having a vertical force, even this one here. So if at all I take moments at a point A, if I take moments at this point A here, I would find my reaction force as 20 on this side. Then by summing up forces in the y direction, I would find the force at the vertical force at point A to be of 10. Then since I have no force in the x direction, that means that we've got no x reaction at this hinge. So after doing that, I come and I take a point such as A, and then I come and I find my internal forces. So at point, if this is the joint A, here I have a force given by N, A, B, then it's also connected to this one here, which would be having an internal force of N A of N at D. Then under it we have a reaction force of 10. So what I'm going to do, I'm first going to resolve this N at B into the Y component and into the X component. For the X, let me just draw it onto this side for simplicity here. So this is N A B in the Y direction, then this is N A B in the X, yeah. So after doing that, I begin by summing up the forces in the Y direction. So when I sum up the forces in the Y direction, I would be having my N A B Y equaling to negative 10. Then knowing my N B Y to be equal to negative 10, I can now come and I use the idea of similar triangles to come and find the value of NAB. But besides using the idea of similar triangles, we can also just observe it from sight that since the triangle here has got a base of 3 meters and then a height of 3 meters, automatically the hypotenuse is supposed to be having a dimension of 3 root 2, isn't it? So with that in mind, I can get to deduce it that that the force that I would be having on the structure, on the member NAB would be given by 10 times root 2. So that one would be giving me NAB equivalent to 14.14 or 14. Yeah, 14.14, which is approximately equal to 14. So after finding that, due to that relationship of the hypotenuse, height, and the base, I know that the force on the height would be equal to the force on the base. Therefore, my NAB in the x direction would also be equal to a negative 10. So therefore, if at all I sum up the forces in the x direction, I would find that my BX plus NAD is supposed to be equal to 0. So my NAD would be equal to, when the NABX crosses the equation, it becomes a negative. So I'd be having negative NABX. By then NABX is negative 10, therefore it becomes a positive 10. So we come and add those forces onto our structure here. So for the sake of NAB, we say that our NAB is equal to negative, actually yeah, it's a negative 14. So here I have negative 14. Then on the NAD, I have a positive 10. So we use the same principle on the remaining joints, and then we shall find that the other internal forces would be of, this would be 10, then this would be a negative 10, and then this one would be having a 20, and then for here we shall be having a 30, then this one would be giving us negative 14, and this slanting, that is CF, would be giving us a negative 28, and then lastly the EF would be giving us a 20. So that is that step 2 for finding the internal forces on the structure. So from that step, we have to go on and find our x1. Then for the sake of x1, we say that we solve it from the equation delta 11 x1 plus delta 1p is supposed to be equal to a 0. From the above, we know that delta 11 would be equal to 1 over EA, not EI for the TRUSS, times summation of N1 times N1, then times the length of the rod itself. So for this case here, like this would be equivalent to 1 over EA into, now we know that this one here has an internal force of 0, this also has a 0, Likewise, this one and this one have a 0. So therefore, we have only 5 of them that are left that have got false on them. So of which, from observation, we can see that this one, and this one have got the same magnitude. So since it's like that, I'll just use the values for a 1 and I multiply by 4. So this should be 4 times our n1 was equal to negative 0.7. Then since I'm multiplying it by itself, I just square it up, then times the corresponding lengths, all of them of a length 3. Then after doing that, I come and I add on now these slanting rods, this one and this one here. So for those ones, they have the internal force. Okay, there are 2 of them, and then they've got the internal force of what? Of magnitude 1. Then since n1 is multiplied twice, I square, then times their length, which is 3 root 2. So this one here gives me a value that is equivalent to 14.37 divided by E A. Then having found this, next we have to go on and find our delta 1p. So for the sake of delta 1p, we know that it's given by delta 1p equals to 1 over EA summation of n1 times np, then times the length of the rod. So this one here would be equivalent to 1 over EA, then into let's first look at the rods which would be cancelling out due to a zero internal moment, sorry, due to the zero internal force. So from observation, you know that this one here has got a 0 on it. So that means that when I multiply this n1 times this np, it would be cancelling out. Likewise, this is a 0, this is a 0, they cancel out. Likewise, this and this one and that one. And then for the sake of this one, this slanting rod has also got a 0. That means that even this one here wouldn't be having any effect on our value. So therefore, we would be left with only 45 of them. So if at all we are to set up our calculation, let me just use a different thing for this time. So if I begin by this one here, by this one, that one we knew that our n1 was negative 0.7, then times here we had a 10, if you remember, times 10, then times this length which is a 3, then plus we go to the next one. Let's say that we go into this one here. That one has also got the value of n1 as negative 0.7, then times the value here we have a 30, and then times the length which is a 3, then plus we move on to the next one. Let's say we move on to this upper one. It also had an internal force of what? Of negative 0.7, then times here we had a value of negative 10, then times its length which is a 3, and then plus the next one. Let's say we do take on this downer one here. It has a value of negative 0.7, then times here we have a positive 20, then times this length which is a 3, and then lastly plus this slanting one here. The n1 is 1, then times negative 14, then times its length, that would be 3 root 2, like that. So when you work out this, we shall find our answer being equivalent to 164.39 divided by EA, like that. So having found our delta 1p and then our delta 11, next we go on and we calculate for the value of what? For the value of x1. Okay, from the equation, delta 11 x1 then plus delta 1p is equal to a 0. My x1 would be equal to negative delta 1p divided by delta 11. So this one here would be giving me a value of the EA and EA would be cancelling. I would be having a 164.39 divided by 14.39. 11.37. This gives me a value of negative 11.44. Sorry, just a little correction. I think this is supposed to be negative. Then if this is a negative, that means that here also have a negative. This would become a positive, therefore my x1 would be a positive. Now for the sake of easily manipulating the final internal forces of reaction, we can tabulate the results into a table like this, like we've labeled all the members, and then in total we have 10 of them. Then we write the corresponding length, then the calculated internal forces as we had found them above, then the internal forces due to the action of the unit load, then we find the N1, N1L, then we get this value here, then that NP, N1L, we also get the value as this. Then from it, our X1 was simply calculated by dividing the NP, N1L divided by N1, N1L to give us the 11.4 as you had got them by calculation. So having got all these results here, now we come and calculate the final internal force by simply summing up the N1, which is this column here, times the X1, then plus the NP. So it ends up giving us the internal forces on each of the members as follows. Yeah, so basically that's how we go about problems concerning the statically indeterminate truss members. Thank you.